All right. Thank you for joining today for this talk on dual encoders. So before I start, I would like to introduce myself because I'm not really a famous celebrity yet. I work at Google, so software engineer. So I'm not a data scientist. I lead a team that builds infrastructure for large language models, which has been the hype recently. Previously, I worked at Booking.com and Databricks in Amsterdam, beautiful city. If you get a chance, do go there. I've also co-authored a book called The Kubernetes Workshop, and I've been open source contributor for some time now. Have some contributions in Git, Pandas, Kinto, Hound, and a few other projects. And I had the opportunity to be a keynote speaker at KubeCon Europe, but that was some time ago, 5 years to be exact. And now I'm getting back into this. So before this talk, I have to admit and have to share a story. I was a bit nervous about this talk, and I was talking to a friend, and he told me a simple hack. And the hack is, he asked me to think of the attendees in a way that some of you will have holes in your socks. That's what he wanted me to think of and not be intimidated by all of you. So can I have a show of hands of those who actually have holes in their socks? That's nice. Very honest. Thank you. Thanks for sharing that. I feel better now. Some days. All right. So let's look at the outline of the talk and see what I'm going to be talking about today. We'll start with a simple problem statement. We'll see how cross encoders can solve them, how they work, and what are the challenges? What are the reasons that we need to look beyond cross encoders? We'll look at dual encoders and see how they work. What are the different types of dual encoders? And again, we'll see if there are any challenges that we face if we try to use dual encoders, and for what type of use cases we face those challenges. And then, of course, we will look at some of the state-of-the-art research and try to formulate some recipes or some ways that we can tackle those challenges. And we'll see how those will apply in different use cases. Before we start, a short disclaimer. I will be sharing whatever I learned on my personal level. So when I say we in this talk, I wouldn't be representing Google. So I just wanted to clarify that. All right. So to begin with, let's start with the problem statement. A super simple problem statement, which is going to be, we have to find similarity between two sentences. Now, who in this room knows at least one way how to solve this? All right. Nice. So I'm going to start with a very naive solution to this, which is going to be keyword matching. What we do in keyword matching, I'll cover briefly, is that we try to match the keywords in the given query to the target, and then we find a similarity score on the basis of how many keywords out of the total are actually matching. Now, the problem with this approach is that it's naive, as I said, and we wouldn't be having this talk if this approach was good and it worked all of the times. So let's look at some examples. We have one example, which is programming for data scientist. That's one query. And then we have a target, which is intro to programming for data scientist. And we know that this approach will work great for this case, because there are all the keywords that are in the query are matching and they exist in the same order in the target. So we know that this approach is great for this. Now let's look at another example, which is programming for data scientist. Again, the same query, but this time we have the target Python for machine learning use cases. And we know that when we talk about programming for data scientist, talking about machine learning use cases and Python, how to use Python for it, is a very related topic, and it should be pretty similar. Any guesses what will happen? Right. So it will not work because all it does is tries to match the keywords and it does not capture any semantic meaning, which we as humans know that it should. Similarly, we have another example where we have bank account on one side, and the other side we have something like bank, river bank. Just an example, I will show you why I took this example. So we know that bank account and river bank have two very different meanings, but this model, this kind of way approach will fail to capture that. So we need something better. And you already got the spoiler alert that it's going to be cross encoders. A cross encoder has just one encoder that takes the input from both query and the target, and it tries to predict a score on the basis of the information that is contained in those two sentences. So it will concatenate the input and target. And when we feed that to the model, this approach is actually called early fusion. What that means is that we are taking two sides of inputs. One is the query and the other is target. And we are trying to have interactions between them before we feed them into the model. And that's why this is called early fusion. So once we feed this into the model, it will perform a full self-attention for that given pair. So we concatenate, we perform self-attention on that sequence. We'll see how the self-attention looks like in a couple of slides. And then it's able to generate a similarity score or a logit in case of classification task. So this is what the architecture looks like on a very high level. I tried to simplify some of the things because the goal here is to capture the high level idea and then see what challenges it brings. So as you can see at the bottom, we have first sentence and the second sentence. We will concatenate those. It becomes one sequence of words. We will tokenize that. So it gives us list of integers where each integer is representing some text that was there in the concatenated sentences. Now, once we have these sequence of tokens, we want to pass it to the token embedder. And the token embedder is going to convert each token in that sequence into its corresponding embedding. And usually we start with some pre-trained token embedder, and we keep these parameters tunable so that as we go in the tuning, it's able to learn what are the better representations of each token. So once we have an embedding for each token in our sequence, we pass it to the encoder, and encoder is this block which is able to look at the sequence of those embeddings and try to come up with a representation that can help us make a final decision about this about the use case that we had, which in this case was finding the similarity between two sentences. So it gives us some combined representation, and then we are able to get the score which represents the similarity for that pair of sentences. So for example, we could have something like bank account on the one side and the other one is river bank, and it's able to predict the score. Now let's look a bit deeper into encoder and see how the self-attention mechanism is working. So this is what's going on inside the encoder. And this is just a small subset of what's going on. So let's look at the bottom layer first. We see that we have a sequence where the left sentence 1 and sentence 2 are concatenated with the separator. So we have bank account, separator, bank, river bank. And you will see that there is a new token added to the front, which is the CLS token. And now the purpose of this token is to represent the embedding that has the meaning from the entire sentence. So what happens in this case is that we have multiple layers. And when we say self-attention, what that means is that each of the token, like let's say we're talking about bank, the first one, it's going to attend to each of the other tokens. And what that means is that it's going to have a chance to get information from all the other tokens, and this will happen in multiple layers. And this is what ensures that the final representation that we have in the CLS token, it's able to retrieve the meaning, the deep meaning, the semantic meaning between the different parts of those two sentences. So that is why when the bank here in front of the account looks at the keyword river, it will know that since this is not a similar word, or this bank is not going to, bank account is not going to be useful in the river context, it will know that it has to score that pair lower in terms of similarity. Now let's look at some of the properties of cross encoders. First of all, as we saw, we have a lot of interaction between each token with all the other tokens in the input. And as the sequence length will increase, the number of tokens will increase, we will have more and more parameters that will need to be learned. So it requires huge computation resources for training and inference. The good thing about that is it's highly accurate because it's able to capture the deep semantic meaning, because it's looking at all of the input for both the sentence 1 and sentence 2, and it's able to capture that meaning and be highly accurate in predicting that similarity score. And it also doesn't require a lot of data, because each example is giving a lot more information in terms of what it needs to learn. So each example is telling it that this is the this is how these different tokens are related, and each example has a huge amount of information for the model to learn so that it can perform better on unseen examples. But this also means that it's prone to overfitting. So we usually use some sort of regularization so that it doesn't overfit with all the different parameters that we have. And to summarize, it's fast to converge because, again, the same reasoning that it doesn't require a lot of data because it already gets a lot of information from each example. It's able to use all of that example to converge faster. But that also means that it's going to be slow at inference time, because every time we perform inference with two sentences, it's going to be going through each of the token and go through all of the self-retention mechanism where it's attending to all the tokens. So it's going to be slower at the inference time. Now let's look at some of the major challenges. We touched upon some of them on the previous slides, but let's just focus on the challenges here. The first one is it requires huge computation resources. And the second one is it's too slow for retrieval and clustering use cases. Now let's define the use cases. We saw that if we are given two sentences, cross encoder is good because it can give us a really enriched representation of that pair and able to give us the similarity. Now, that is when we have two sentences. What if we have 10,000 sentences that we want to compare and see how they match up against each other? So if we try to do such kind of clustering, it's going to take a lot of time, because if we are trying to cluster 10,000 examples, 10,000 sentences, it's going to, we will have to compare each sentence with every other sentence and do the inference with the cross-encoder model every time. And it takes in order of tens of hours to do that. And don't quote me on that, because I intentionally put it like that, because it really depends on what machine you have and what kind of resources you're putting in, but it takes a long time. Now, let's say you have another use case, which is retrieval. So in this case, let's say you have 10 million examples. Let's take a concrete example. So you have a set of queries and you have a set of documents that you want to match. And you might have documents around maybe 1 million, 10 million, or maybe even 100 million. And what you want to do is, for a given query, you want to predict what are the top results that match this given query. If we use cross encoder for that, we can definitely use it. What it's going to do is it's going to compare that given query with each of the 10 million possible documents, try to predict a similarity score, and then sort based on the similarity score to actually get the results, get the top N results matching that query. And also, again, it takes a long time. So it's not really a good idea to use cross encoders when you have that kind of a problem statement where you want to retrieve top N results from a large number of candidates. Now, we want to solve this. And I think you already had the spoiler to this also, because the talk is called dual encoder. So we'll try to see what is dual encoder and how it can help us solve the issue that we just saw. So as the name suggests, we have two encoders in this dual encoder network. Each encoder is going to be for one side of input. So if we have query on the input side, and we want to predict the target, it will have two encoders, one for each of the inputs. It's again going to perform self-attention in the similar way that we saw previously, but it's going to keep the self-attention between input and the target separate this time. It's not going to have interactions between the two, and we'll see on a later slide what it looks like. So once it performs self-attention, it will come up with an embedding that will represent an input and the target. And then we can use those embeddings in different ways. We can use some sort of similarity scoring, which could be like cosine similarity, Manhattan distance, or Euclidean, different ways to compute the similarity based on a high dimension embedding. Or we can also use them to do classification. So we can cache those results and perform some other model on top of that or maybe recommendation systems can also build on top of the embeddings that are created from dual encoders. Let's look at the model again on a higher level. So in this case, you can see there are two different towers. These are usually called towers or networks. And what happens here is that we have sentence one. It's going to go through the token embedded for the same reason that we covered previously for cross encoder, goes into the encoder. Then there is a projection layer, which converts the encoder output to a certain dimension that we can choose. And then that is going to be the dimension for the embedding that is created as a result of this one sentence. And the same will happen for the second sentence. It goes to token embedder, encoder, projection layer, and convert it into a fixed size embedding. Now we have these embeddings. We can do the similarity scoring on top of that. And usually it's cosine similarity, just take a dot product of the two embeddings and come up with a score that's going to tell you how similar these two embeddings are. So we can see here that there is no interaction between the two towers at all until the point where we already have the embeddings and we are ready to do some similarity scoring. Now let's see what goes on inside this model. There is a self-attention mechanism which looks like this. In this case, as you can see, we again have the first query, which is bank account. There is a CLS token, which is going to represent the entire meaning of the rest of the sequence. And similarly, there is a second tower, which is going to be performing the same kind of self-attention, attending to all the different tokens, but only within that particular sentence. So it's not going to look into what is there in the first sentence. And once we have the final representations from the CLS tokens, we are able to compute the similarity. And again, the same thing that we have a similarity score and we are able to either train the model or find out the similarity in production. Now, let's say we have a dual encoder trained. How will it actually work? I want to cover a workflow where we want to see how this actually works in production. So the use case that we have here is that the same use case that I described earlier. We have a set of queries, we have a set of targets, and we want to know what are the top end results from these documents for each of the given query. Now, what happens in production is slightly different. Usually we don't have a set of queries that we want to predict the responses for. What we have is just a single query that the user enters, and we want to find out the top end results for that single query. So what happens is we run a dual encoder for serving. I won't go into the details of like how you can optimize that. We will run offline inference for all the target candidates. So in that case, we had like 10 million documents that we have to choose from. We will run the inference to generate the embeddings for all of those target candidates and store the embeddings. Next, we are going to create a nearest neighbor search index. There are a few open source ways to do it. Like some of them are like scan or span. Span is actually an approximate nearest neighbor search. And then once we have all of that, we are going to run the online inference on a given query and retrieve the top and nearest neighbors from the index corresponding to that embedding. So in short, what happens is that there are two things going on with the dual encoder in production. One is the offline approach, where we are caching all the embeddings for all of the target candidates that we have. And we create some sort of index that allows us to search for the nearest neighbors based on those high dimension embeddings. And we just keep that. And on the other side, when the user is running a query, we will serve that query to the dual encoder by real time, generate the embeddings, compare, look for the nearest neighbors, and give out the results to whatever use case there is, whatever product or feature we are empowering with this. Let's look at some of the properties. It produces an embedding representation of the inputs. And this is something that was missing from the cross encoders, because cross encoder was taking the combined input. It had no way to distinguish between the two inputs after the encoding step. But in this case, we actually generate the embedding that we can use for a lot of different use cases. The inference is faster. And the reason for that is because we have this offline inference step, which we are using to compute and cache all the embeddings. And the only thing we are doing in real time is running the dual encoder on a single query that the user enters. And as I said earlier, it's possible to cache the output embeddings. It requires a lot of training data though. And the reason is clear in how the network works. So we have these two different towers, one for the query and one for the document. And there is no way that they are interacting. So what needs to happen for a model to work is that the left tower, the query tower, is going to be able to generate a representation of the query, which is aligned with the representation that the other tower generates. And it's not an easy problem because when we have these independent networks, it's very hard for us to make the dual encoder learn faster. And that's why we need a lot of training data to make sure that we're able to get a good performance. Now, that's the spoiler alert. It comes at a cost. It's worse in terms of performance than a cross encoder. So we have a trade-off. But before that, let's look at different types of dual encoders. We have this part of the presentation is actually based on the research that was performed by my colleagues at Google. So I'm really proud to be presenting their work here. The first type we have is CMEs or symmetric dual encoder. We'll see what these are on the next slides. We have asymmetric dual encoder. So these are the two primary types, but then we have some variations, some special variations that we can use in certain use cases, like asymmetric dual encoder with shared token embedder, with frozen token embedder, or shared projection layer. We'll see what all of these mean. So first of all, let's look at the symmetric dual encoder. Now, this is what it looks like. And you might think that this is very similar to what we saw in case of cross encoder, that it also had one token embedder, had one encoder. It did not have the projection layer, but the model part was very similar. Now, it's not similar at all because we have major differences here. The first difference is that there is no concatenation. So each of the inputs are going into the model separately, one by one. And there is a projection layer that generates a fixed dimension embedding for each of them separately. So these are the two differences. First of all, we don't have that early fusion. And the second is that the output of the encoder actually going to give us the representations of the two sides. And then, of course, we have some sort of similarity function on top of that the set of embeddings. Now, this is actually a pretty useful setup. The reason for that is the number of parameters in this case are smaller because all the parameters are shared between both the left tower and the right tower. So you have less parameters to learn, and it's easier to train and requires less amount of data. But there are cases when you don't want that, when you don't want to have a shared encoder or shared model, shared network. And some of the use cases like that could be that you have question on one side, you have answer on the other side, but the answer is going to be way, way longer than the question. The question can be like 1 or 2 sentences, but the answer in this case maybe has a paragraph with maybe 50 or 100 sentences. So what you want in that case is you want to have different encoders with different sizes so that you're able to capture the complexity of the answer, but you don't want to pay that cost for the question tower. So you want to keep that smaller. So let's look at what it looks like. That is the asymmetric dual encoder. As you can see, this is the case that we saw earlier where you have separate towers, token embedder is separate, encoders and projection layers are also separate from each other, and there's no way to interact until we get to the similarity, until we compute that similarity between the embeddings. Now, this is nice, but there are challenges. Research says that the asymmetric dual encoder performs worse than the symmetric dual encoder. And there are no surprises there because we have such different parameters. First of all, we have a lot more parameters, almost double, and it's harder to train that model. And the number two is also that it's possible that the left tower is computing the embedding in a different projection space than the right tower. And that is a problem because we don't want that. We want these to capture the semantic meanings in a similar projection so that we can actually say that if these two embeddings are closer, that means these two sentences are actually similar. So we try to solve this problem by making some small changes to the architecture. The first one is asymmetric dual encoder with shared token embedder. This was an attempt to make the asymmetric dual encoder perform better and closer to the symmetric dual encoder. What we do in this case is just the token embedder is shared and it's tunable, and the rest of the network stays the same. Another variation of this is when we, instead of sharing, we just freeze the token embedder so that we have pre-trained embeddings for each of the token, and it's not going to be learned during the training. But what we saw is that both of these changes don't really make a lot of difference. They are definitely better than what we have with the asymmetric dual encoder, but it's nowhere comparable to the symmetric dual encoder. So it doesn't mean that we should discard the asymmetric dual encoder and always use symmetric. Not really, because then the third thing that they tried is having a shared projection layer. So remember the main issue. No, so the main issue with the asymmetric dual encoder was that there is a big chance that the two embeddings are in different projection space. So what if we have a shared projection layer to keep the two embeddings in a similar space so that their similarity actually implies a similarity in the meaning of two sentences. So this is what it looks like. We have a projection layer that is shared. It's also going to be tuned with the training. And we see that this change is actually able to bring the similarity of asymmetric dual encoder very close to symmetric dual encoder. Now, of course, dual encoders are not perfect, and there are some challenges. The first one is the lower performance. As I covered earlier, that it's worse to use a dual encoder in terms of pure performance when it comes to comparing with cross encoders. And the other one is it requires a lot of data. And another issue is that it's actually difficult to acquire the data where we can have a query and the corresponding matching documents. So let's see how we can solve these issues with some of the research that has been published recently. So to solve these issues, we need two things. We need the best of both worlds. We need the faster inference that comes from dual encoder, and we need the better quality that comes from the cross encoders. And let's see how we can do that. The first method that has been proposed is using cross encoder as a teacher model and dual encoder as a student. So what this means is you train a cross encoder using whatever training data you have. Then you label the larger data set that is required to train dual encoder using this cross encoder. So that is what it means for a model to be a teacher model, that it's generating the labels for a data that is going to be used for training another model, which is called student model. So that's what we do. We use that label data to train a dual encoder model. And this way we are able to solve one problem, which is dual encoders require a large amount of data, and it's difficult to acquire that. So we are tackling that problem with this one. Another approach is combining the dual encoder and cross encoder in one network. Not in one network, but in one system. So what that means is we train dual encoder and cross encoder. We use the dual encoder first to retrieve the top K results, because that's what dual encoders are really good at. Then we use cross encoder to compute the similarities between all the pairs with the query and all the K results that the dual encoder gave us. And we're able to use the higher accuracy of cross encoders to actually discard the results that are not really good and have better ranking of those results. This is what it looks like. And I stole this from a blog post. What it does is, as I said, that we have a collection of documents. We use the dual encoder to retrieve some candidates. And then we use the ranking re-ranker cross encoder to actually compute the similarities again, because we don't really trust the dual encoder accuracy to be like higher than cross encoder. So we are able to get the re-ranked results from the cross encoder. So this is like combining the powers of both of the networks in one system. And of course, it's going to be difficult to train them because now we are training two models instead of one, but at least in production, we are able to get better results by having this combination. And in this case, cross encoder doesn't have to go through all of the examples. It only has to go through the top K examples that dual encoder retrieved. Another approach that has been proposed, I call it hybrid approach. In the paper, they suggest a name, poly encoders. So what happens here is that we have cross attention at the end once we have the two embeddings. So earlier with the dual encoder, what we were doing was we were only computing the similarity score and just use that as the golden label. But in this case, what we're doing is after we have the embeddings, we are going to have some sort of attention mechanism between those two so that it's able to learn more parameters and it's able to gain some of the accuracy that comes from cross attention when we have cross encoders, when we have attention between the two inputs, between the two inputs. And as a result, we get better performance. Let's look at the network. It has a lot of details, so I want to focus on what I want to share. So let's replace all of that with the query encoder, all of that with the candidate encoder. And this is what a typical dual encoder looks like. And similarly, we're going to simplify things and say that this is what a cross encoder looks like. We give it a sequence of tokens and we get a score as an output. Now, what this paper proposes is that we are going to combine these two. And this is what it looks like in the end. We have a query encoder and it has no interaction with the candidate encoder. But once we have the embedding representations from both these encoders, we have a cross attention, small cross attention network that's able to capture meanings in a better way from those representations and compute a score later on. All right, so we looked at some of the ways that we can solve those challenges. Now let's quickly cover how we can evaluate dual encoders. The most popular way that we usually evaluate the dual encoders is using offline retrieval evaluation. What that means is that we have some set of data which says that for this query, this is the target that actually matches. For another query, this is the target, and we have a lot of these pairs. And what we will do is very similar to what we do in production. We'll compute the target embeddings for all of the targets on the right side, store them, and compute the embeddings for the left side, also store them, and now have a compute the similarity and see what similarity the dual encoder assigns. And there are some metrics that we use that are not used in other kinds of tasks. One of them is MRR, which is the mean reciprocal rank. This metric covers the or represents the information that if a dual encoder is predicting n results, let's say top 5 results, we want to see in these 5 results, where is the result that we actually saw in the training, or which is the actual true label. And this metric tells us that exactly that information. So lower the MRR, that indicates that the results that were actually true were ranked at the bottom. So it could be 5th result or 4th result, but the higher it is, it represents that the true target was actually 1st or 2nd or maybe even 3rd. Another metric that we have is the recall. And this is a simple metric. All we look at is for n equal to 1, we look at recall at 1, which means that the top 1 result that the dual encoder produces, is that the right target or not? And similarly, we have other metrics like recall at 5, recall at 10, recall at 100, depending on the use case. We can see what metrics make sense to track and to evaluate on. All right, so let's do a quick recap. Yeah, don't have a lot of time, so a quick one. We looked at the cross encoders. We saw how it has one encoder, generates the embedding, generates the output score. And we also saw why it's not really good for retrieval. Like it takes a lot of time because it has to compare all the different pairs together. And then we saw how dual encoders can solve that problem by caching the results, the embeddings from one side, and only do a nearest neighbor search once we have the embedding for the query. We also saw the different types of encoders, asymmetric, symmetric, and we saw why asymmetric is not really good, and we have to make some changes to it. And we saw that sharing or freezing the token embedder was not really good. It didn't really give us better results, but sharing the projection layer gave us a lot of improvements, which made it comparable with the symmetric. Next, we looked at some of the challenges of dual encoders, and then we looked at some ways that the recent research has been trying to fix those challenges. And yeah, I'm not go through them again. All right, so thanks a lot for paying attention. And now we have a few minutes left for any questions that you might have.